Apart from the first two chapters of the video series, there is not a mention of group action in the series for a good reason, as we will see. Let's revisit what we have said about group action in the first video. A group action is where a group of symmetries act on a set, usually of vertices, edges, or faces, to give the same set back. And we often use the example of a particular rotational symmetry of the regular tetrahedron to explain the concept. Let's use another example of the group of symmetries of a regular octagon acting on a set of vertices. If we denote r as the anti-clockwise rotation by 45 degrees, then r acting on 1 will give 2, acting on 2 will give 3, and so on. Note that the output, which is the rightmost column, is just a rearrangement of the input, which is the middle column. This is not a coincidence, and it comes straight from the definition of a symmetry, because in this case, a symmetry preserves the octagon, and so the vertices as well. So acting any symmetry on the vertices would just rearrange them. This means if we discard the octagon and leave only the vertices behind, then every symmetry will correspond to some rearrangement of the vertices. However, not every rearrangement will correspond to a symmetry. For example, this rearrangement of swapping the two vertices will result in this octagon, and I don't think we want to call it a symmetry. Still, it is more convenient to consider all these rearrangements, not just some of them. This is more officially named permutation. So now we have established that all symmetries can correspond to a permutation of the vertices, but not necessarily the other way around. The reason why we consider permutations is that in some sense it is still a symmetry. After all, if we discard the notion of distances, then a permutation like this one would preserve the object, just that the object in consideration is the collection of the 8 vertices. And in fact, all the core properties of symmetries as discussed in the first video would also hold if you replace the word symmetry by permutation. Hence, the permutations would form a group. But for some reason, it is confusingly named symmetric group, even though it is not about symmetries. So to summarize what we have so far, we have a group of symmetries of an octagon acting on the set of vertices. For every symmetry, say the horizontal reflection, we can always discard the figure and just look at how the symmetry acts on the vertices itself, which means all symmetries correspond to a permutation. This correspondence is more formally constructed as a function, say phi. This function sends an element from the group of symmetries to something from the symmetric group of the set of vertices. It looks complicated, but what this function does is simply sending any symmetry G, say a horizontal reflection in this illustration, to the corresponding permutation, which we just abbreviate as G star. However, this function is not just a normal function, it is specifically a homomorphism. Why? Consider phi of h, phi of g, which means that we are doing the permutation corresponding to g first, then do the permutation corresponding to h. This is a permutation corresponding to the symmetry hg. So this is just phi of hg. So it fulfills the definition of homomorphism that we discussed in the previous video in this series. In short, whenever you have an action of a group of symmetries G on a set X, you will have a homomorphism from G to the symmetric group, which is the collection of all permutations of elements in the set X. Here, we just use the example where G is the group of symmetries of an octagon, and the set X is the set of the 8 vertices. And this correspondence between an action and a homomorphism will hold in general. This correspondence between the two concepts is very useful, because previously to analyze a group action, we only have the orbit-stabiliser theorem as a tool. but because we link it to a homomorphism, we also have the tools described in the last video, i.e. the isomorphism theorem. A very direct application of this change in perspective is the proof of Cayley's theorem. Before we move on, I just want to point out that everything from now on, like the set that G acts on, can be more abstract than just vertices. But it is still very useful to have this mental picture where the elements in the abstract set X are just these little dots, and a group action just somehow rearranges these dots. With that said, let's look at what Cayley's theorem says. Cayley's theorem states that every group G is isomorphic to a subgroup of the symmetric group of G. Looking at the correspondence once again, it looks like the set X is the group G itself, which is quite different from what we did, but the action we will be considering is very simple. If we act G1 on the symmetry G2, then we just get the symmetry corresponding to doing G2 first, then G1. So going back to the visualization of group actions using these colorful dots, each dot now represents a symmetry. So one dot would represent the identity symmetry, and one dot would represent the symmetry G, and there would also be its inverse somewhere, and we also might have another symmetry H, and then we would have GH and so on. Because the action we defined has this form, when we consider the action of G on these symmetries, the identity would become G itself because doing identity symmetry first, then G is the same as doing G altogether. Then G inverse would be sent to the identity because undoing G then do G is the same as doing nothing, that is the identity. Then the action of G on other symmetries would look something like this. So now, every single symmetry, say H, corresponds to a permutation of these dots, which are symmetries themselves. This looks like we have already proved Cayley's theorem because we showed that every symmetry will correspond to a permutation of these symmetries, but there is still one very subtle thing to consider. Even though every symmetry will correspond to a permutation, it can happen that two symmetries can correspond to the same permutation, in which case the theorem does not necessarily hold. Luckily, in this particular case, we can show that this cannot happen. The trick is to see where the identity goes. If we are considering the permutation corresponding to the symmetry G, then the identity will be sent to symmetry G. If, however, we are considering the action of H, then the identity would be sent to H instead. In other words, the worries that we had were unnecessary because different symmetries would correspond to different permutations. A more rigorous way to prove Cayley's theorem rather than moving the dots around is to use the isomorphism theorem on the corresponding homomorphism. You can show that the kernel is a set only including the identity. And as part of the isomorphism theorem, the image has to be a subgroup of the symmetric group. Next, you can show further that this quotient group is isomorphic to G by constructing an isomorphism directly. This theorem provides a motivation for studying symmetric groups in particular. If we can study all the subgroups of a symmetric group, then we will have studied all the possible groups as well. This is why most courses will continue to include symmetric groups as well. However, even though symmetric groups would be a big topic in group theory, I would put an end to this video series because most concepts in symmetric groups as listed here are very algebraic. Even for something seemingly simple like the sign of permutations, which is literally just whether it is positive or negative, the justification for such an assignment is not intuitive. So for this topic of symmetric groups at least, I don't think I could bring some very unique insights and intuition to YouTube, especially when a quick search reveals that a lot of YouTube channels talking about symmetric groups are available. But on the upside, the next videos would be first a summary of the entire video series, including a very cool example to illustrate all the concepts covered in the video series, which should be out in a few days. And then a second video on coronavirus, but this time not about the SIR model, but the stochastic process known as branching process. Then I will release yet another group theory video, but this time not essence anymore, because it is an application of the orbit-stabiliser theorem. After that, I don't have a very solid plan now, so leave a comment for some topics for me to cover. Even if you don't have a request, leave a comment anyway. If you enjoyed this video, give it a like and subscribe to the channel with notifications on. See you next time!